Hi, everyone. This is the Chromium IPC 101 talk, Introduction to Mojo. If you're not familiar with the term IPC, this is inter-process communication. This is how Chrome's many different processes talk to each other. It's going to be two halves. I'm going to give a high-level overview of some concepts with some examples, and then Oksana is going to dive into some of the details. Just as a reminder, I see it's already on the screen. So Slido, ask questions on Slido. All right, just to jump right into it, a little background. I think probably this track had a multi-process architecture talk already on the first day, but just as a recap, Chrome runs many different processes in the operating system. This is because we don't always trust them. For example, renders process a lot of unsafe data, easily exploited. So we sandbox them heavily, and so they can't do things like have direct disk access or direct network access. They have to kind of be brokered through somebody who we trust more. So we need some mechanism for safely communicating between these processes since they're isolated from each other. The other little bit of background, especially if you're new to C++ in Chromium or just Chromium in general, we do a lot of asynchronous work in Chromium, and it's facilitated by this scheduler and a set of related APIs. You see a lot of post tasks, a lot of bind once. These are callbacks, tasks. It's ubiquitous across the tree, and Mojo relies heavily on these things. So IPC is an inherently asynchronous work. You ask another process to do something. You don't want to sit around and wait for it to finish. You just want to say, please do this and let me know when you're done. And so this is a non-Mojo simple example of the same kind of concept where we schedule some very expensive arithmetic operation on a background thread, and then we get the result scheduled as a callback back on our thread whenever it's done. So just as a really quick introduction, this is asynchronous programming in Chromium. It's everywhere. So with that, we'll take a quick look at Mojon. If you look around the tree, code search, whatever, you will find lots of .mojon files. That is what this language is. It's describing IPC interfaces. So if you see a Mojon file, chances are the definitions there are used somewhere in some message between one process and another. In this case, we have a really simple interface for a calculator. It defines some operations. For example, you can add two numbers, and the reply will contain the sum of those two numbers. You don't really need to understand the syntax or worry about it too much. This is just to introduce the concept that interfaces exist, and we'll use this calculator interface as a reference for the next couple of slides. So the basic idea behind Mojo is it allows us to schedule this async work in another process. It looks just like an async method call. You know, I call add on this object, this remote calculator, which we'll talk about in a minute. And eventually the result comes back to a callback we provide. What Mojo facilitates is this asynchronous work being done somewhere other than the process that called it. So there's some implementation of the same calculator interface sitting somewhere. And when you call this add method, the browser will eventually schedule a task on the calculator implementation to run that add method with the arguments that you provided. And when it runs its callback, the net result is, again, facilitated by Mojo. A task will be scheduled in the renderer to run the callback that was originally provided by the caller. And the idea behind Mojo is just kind of make this whole thing easy. It makes inter-process work kind of feel just like any other asynchronous work you might do in Chromium. And so the two key types that we use to support this, and Mojo has a lot of types and a lot of APIs, but these are the two really important ones. Most Mojo usage you see will use just these two types. Some key points here. Remote is what you use to make method calls on an object that might live somewhere else. Receiver is what you use to receive those calls and link them to a concrete implementation that generally lives next to the receiver or owns the receiver. And then finally, each remote is exclusively entangled with a single receiver. You don't have a remote that can send its messages to many different places. If you use a remote and it sends a message to a receiver, every other message it sends is going to arrive at the same receiver in the same order. So as a really brief example, we have a remote here, default constructed remote. This is valid code. You can default construct a remote. but it's not usable. It's very similar to a null pointer. If you try to dereference it, you'll crash. Maybe you want to crash, probably not. But it's very easy to turn this into a usable object by binding it. And the most common and convenient way to bind a remote is to call this very long function named bind new pipe and pass receiver. What this does is it turns the remote into a real functional remote that is what we call in a bound state, which means you can immediately start making calls on it, like this add call. It also returns what is called a pending receiver, which is almost a receiver, but not quite. But it is entangled with the remote, kind of permanently entangled with the remote. So any call that's made on the remote is going to arrive at this pending receiver. Now, pending receiver is an inert object. It doesn't actually do anything, but what we can do is we can pass it on to a real receiver, which links that endpoint with a concrete implementation. And so if we do this in a single process, if we write this code, what will actually happen is that call to remote add will essentially result in a task being scheduled on the calculator impl to add those two arguments and respond with a result. So it's just a fancy way of scheduling a task whenever you're using it in process. But one very important point is that this pending receiver object that we've returned is trivially able to be passed to another process where the same code you see down below could be written instead. So the basic idea here is if you're a client of this calculator interface, you write this code to have a remote, you bind it, you call whatever you want on it. And you don't really worry about where the receiver is going to end up. You send it somewhere, it eventually gets hooked up to an implementation like below, and tasks start getting scheduled on the implementation. And so here's a concrete example. This is a real web API. You can copy some files. Here's a really advanced website that lets you copy files by clicking a button. And when you click that button, Blink is going to run some code to copy a file on disk. But because Blink is running in a renderer, and we definitely don't trust renderers, renderers have no access to disk. They cannot directly manipulate the file system. So they have to ask the browser to do the work for them. So this is where Mojo comes in. The renderer sends an IPC to the browser and asks it to copy some files. The browser knows who the renderer is, so maybe it decides the renderer is not allowed to copy those files and it says no. But supposing that it's allowed, the renderer will go on and ask the operating system to do the work. It'll get a response. It'll respond back to the renderer with that response, and the renderer will do something with it that will result in some page event or something like that. And so this is really common for web APIs. You make a web API call, it turns into an IPC to the browser, a response eventually comes back, and this bubbles up to either maybe an event, a DOM event, or a promise gets resolved or something like that. Really common. And this is just one example of it. And so to implement this, we need some interface for the renderer to ask the browser to copy a file. And so this is a real interface. It's defined inside some Blink Mojon somewhere. And it has a bunch of other methods, but one of the methods is copy. It takes two URLs, returns an error code indicating whether it was successful or if not, why. Again, don't need to worry too much about the details of this definition, but it exists. This is a real interface. And the renderer side code to facilitate this operation, to initiate the file copy, is very similar to what we did with the calculator. It's just you create a remote, you bind it, and you call your copy. The only difference is instead of that receiver going to some local implementation of File System Manager, we've passed it to this new API called Get Interface, or Get Browser Interface Broker, Get Interface. Browser Interface Broker is a generic interface we have between every renderer and the browser that allows you to sort of pass any pending receiver you want over to the browser, where we have some common code that's audited by security and relatively easy to maintain, which decides what implementation to hook the receiver up to inside the browser process. And so render side code looks like this, just like if we were passing the receiver in process or whatever. Nothing changes here. The important point is if you want to get a receiver to the browser, you just need this API. Now, from here, Oksana is going to talk about what happens in the browser, what code gets generated, and some other details about how to use Mojo.
Thank you, Ken. So the C++ code is generated from the Mojon IDL during the build process. Let's take a look at the generated code for the file system manager interface. Among other things, this class has a pure virtual copy method, which any implementations must override. The method has a source path and destination path input parameters, and it also takes a callback to run on the return value. Okay, so to implement our interface, we need to inherit a class from file system manager that we just saw. The minimal implementation would override the copy method and have a receiver instance to handle the communication with the renderer. Let's take a look at a possible implementation for our class. First, we need to set up the receiver so that it can start accepting messages and translating them into method calls. A common pattern is to have a constructor that takes a pending receiver as a parameter and then uses it to initialize the class's receiver instance. So the pending receiver that we send from the renderer will become tied to this implementation. We also need to implement the copy method. For example, we can call some other code to copy the file and get a result, and then this result is passed to the callback, which will run in the renderer. So at this point, our file system manager implementation knows what to do with the pending receiver, but where does it get one? So you might remember the browser interface broker mechanism mentioned earlier. The browser part of the broker maintains the map that matches pending receivers for different interfaces to their relevant implementations. Since the renderer uses the frames broker to acquire the file system manager interface, it would be reasonable to have a method in render frame host impl, and this method will create an instance of file system manager impl and pass the incoming pending receiver to its constructor. And finally, we register this method in the broker's map so that it gets called when the renderer requests this interface. So here's a very basic diagram of everything we just looked at. If we zoom out, so it shows how the pending receiver travels from Blink code to a browser interface broker in the renderer to across the process boundary, and then in the browser from the binder map to the render frame host impl method, and then to file system manager impl constructor, and then ends up being connected to the receiver. So when the Blink code calls copy on the remote, the receiver in the browser calls the appropriate implementation method. So this is simplified, but fairly close to the real code, since all the necessary parts are there. And this way of communication can give us a lot of power. So how do we make sure it's secure? So let's take another look at our copy method, specifically at its input parameters. We could have used strings for the source and destination paths, but then the renderer could potentially pass some data that would trigger vulnerabilities in the browser. So instead, we went with a safer approach and used the provided Mojon URL type because it has built-in validation. A message is only considered deserialized if it's valid, and only then will Mojo invoke the implementation. Otherwise, it signals an error and the receiver is disconnected. So the browser implementation can be sure it's always called with a valid URL. It's easy to plug in your own validation as well. So message validation is one way to make IPC more secure. We use other approaches. As mentioned, only the browser process is trusted by default. So if parts of Chromium want to communicate using IPC, the browser handles this communication. And whenever we make changes to Mojon files, someone from the security team has to approve them. Pre-submit checks in commit queue make sure this happens. So we have looked at fairly simple examples and covered the very basics of Mojo IPC, and we're leaving you with some resources you can use to learn more and be productive. So go/mojo-docs and go/mojo-basics point to markdown docs in the Mojo source directory. Mojo and services section in the top level docs gathers related links. And if you have any questions, please don't hesitate to contact us. Follow go/mojo-slack to join our dedicated Slack channel in the Chromium workspace, or email us at chromium-mojo@chromium.org. And finally, Chromium Code Search supports Mojo file indexing. That's cs.chromium.org. chromium.org. Thank you.
Yep. Watching Slido. If there are no questions on Slido, we'll give it another minute or two. If there are no questions, we'll also be in the hallway track for about 15 minutes after this, and you can feel free to ask any live questions there. I don't.
Yeah, thank you for mentioning the full link.
That's a good question. We could certainly prepare an hour or more talk, but you know, we I think we were just budgeted a half hour for this, and so we tried to focus on a very high level approach. There's a lot of details that you don't need to understand to just use the basics of Mojo, and so we were kind of hoping to just provide a basic introduction so that you know, people can have a working knowledge of it. In general, while there's a lot of complexity under the hood, we really actually try to make it quite simple to use. So hopefully it's not too complicated just to do the basics of, you know, making a call from here to there. Yeah, right. Okay, so oh yeah, okay. So they are queued in the pending receiver. They're not exposed. It's kind of completely opaque. It's deep inside some internal Mojo layer. But that pending receiver is essentially, it encapsulates the ownership of the receiving message queue. So wherever you pass it, the queue follows. No, the queue is not backed by shared memory. The messages are copied as if the connection had already been established across the process. The messages will then just move across the process boundary as if you waited until it was established and then sent them. So that does imply that there's some extra copying in these cases. Generally, the pattern is you create the pipe and you start queuing messages immediately, and you also send the receiver pretty much immediately. So, it's not fully deterministic behavior, but in general, some of those initial messages will be copied. They'll be serialized and put in memory in the sending process. They'll be queued, and then whenever that receiver makes its way to the other process, the messages will also be transferred. But no, we don't use share. Actually, there is work underway to use shared memory as a transport for all messages on some platforms, on Chrome OS and Linux at least, where there's like a eventfd, I don't actually know, I'm not implementing it. Some Futex, memfd, eventfd combination of APIs where we can use a shared memory ring buffer in each direction to just sort of quickly swap messages into the other process, similar to what Binder does on Android. Renderer is not part of graphics. No, so it is a little bit of a misnomer. It renders web pages. So a renderer process is responsible for parsing HTML, parsing JavaScript, parsing images, conceptually composing all of the page contents together and sticking them in a rectangle of pixels on the screen, processing user input, etc. So any JavaScript web API that you call is running in a renderer process. And so if you try to fetch a URL or something, that's ultimately going to go to the browser and ask it to do a network operation, and then it's going to come back to the render and say, here's your socket. No, there's no notification like that. It's just part of the process of setting the pending receiver, is its queue gets sent along with it. And so if there's messages in flight, they'll follow, but it's completely hidden. So as a user of the system, you just pass the pending receiver and bind it somewhere, and all the messages that were sent arrive where they're supposed to. I think that's all the time we have for questions here. We'll be in the hallway afterwards for any other questions you would like to ask. And I think that's it for me. Oksana, did you have anything to add?
No, thanks everyone for the attention and for the questions.
Thanks.